Good morning, everybody. I'm Ilkay Altintas. As Mike mentioned, I lead our data science efforts to coordinate them. Today, in particular, I'll talk to you about our relatively new Data Science Hub initiative. And in the hub, we definitely noticed we are doing a lot of applications that span computational science, data science, and the advanced infrastructure that SDSC is known for. And we are now building a new data gateway that is a solution architecture and set of services for building data science applications for your science. So the emphasis here is really the science and the questions that you would like or anyone would like to work with. And we are looking to work with the community at large in data sciences and computational sciences to enable their middleware, their tools and applications work through this environment. So it's a hub-based environment that brings together methods and technology experts with people who are trying to do the science and enable everyone to connect with each other and work collaboratively on today's biggest challenges. And of course, we have our collaborative experts and services ourselves on deep learning and AI that you'll be hearing from mine one today. And machine learning at large and blockchain. We have Suba here for Open Science Chain, and we have a block lab that's newly forming. They can talk to you about that. We have IoT applications, information visualization applications. Ilya Zaslavsky sitting here, he can also talk to you about those. And we have a plethora of solutions for data management and data engineering services that span across NoSQL and SQL platforms and structured, unstructured data and different big data platforms. So, what we'd like to emphasize here is platforms. Platforms that enable people, platforms that enable applications, platforms that bridge technology to applications. And we are using our systems as a lab, or so to say, the test bed for these solutions. But we are happy to connect with the rest of you on platforms to make sure we connect and we build applications together. And also for our industry audience, we have a number of different industry engagement programs under the Data Science Hub and SDSC at large, and we'd like to talk to you more about as well. But overall, I say, if data science is the deep religion, this thing is its temple. And that's really about solutions and services and applications. And on the UC San Diego front, we also had a recent donation over the last couple of years by one of our alumni, Halıcıoğlu, and we formed a new institute, Halıcıoğlu Data Science Institute. At SDSC, we collaborate with them, and the Data Science Hub is actually a cross-cutting initiative between this UCSD initiative and the SDSC's own solutions and platforms. What's the common theme here? Everything I said, the common theme was definitely the applications, but applications around big data, computational science, infrastructure, advanced cyber infrastructure, and the data science methods and solutions themselves. And why is that so? Because in most of these applications, you need everything. These days, we can't do science that doesn't have big data and big compute that we call a grand challenge. And when you put these together, our ability to measure ourselves, our environment, everything that we have in our mind, and combine it with on-demand computing at scale, we have a new set of applications we can enable. These we call dynamic data-driven applications. So it includes data and steering based on data, together with what we know about our environment, what we know about the sciences, and the scientific models that we've been working on until now. So it's not by surprise then. We have age-old disciplines like manufacturing and the cities and the power management and medicine They all have these new names like smart and precision and personalized and you name it. What's the difference here? It's the data. It's the sensor. If something is smart because there's a sensor in it. My smartphone is smart because there's a sensor in it. Medicine is personalized because we talk about actually individual patients now and their history, what they are doing, their daily activities, their habits, along with their medical history and genetics. So all this combination of lots of data we are collecting and people's habits changing about how much data they are sharing, it contributes to one thing, to the big data, or the code name for all the data in the world now is big data. And big data is nothing but data coming from all sorts of untraditional sources combined with traditional structured data approaches, data warehouses. And I love this picture because it says 10 to the power 21, and this galaxy in the middle is not by mistake. Actually, if you scale to the universe 10 to the power 21 times, you actually get Milky Way. And when you think about it, we are now going for an environment that we have a galaxy of data and we have to find our way through it. So you need new types of ways to think about data when you have that. You can't just expect to have the data and use it as it is. We need to do some things. We need to do things that actually amplify the value of data, and that's data science. You need to take the data, you need to optimize HPC and big data, so you can actually come up with different metrics, metadata, understanding about these data sets, and to reduce forms that we can call high-value data sets. When you have high-value data sets, what you would have is more communities using these data sets through these gateway environments. You can aggregate it with further data sets if you solve the challenges related to using these individual data sets and what they mean for applications at large. And also you can commoditize looking at these data sets. You can actually build visualization environments, information querying environments that you can discover, access, and do something with these data sets at a lower resolution form in a way that bridges you to higher resolution forms if you need to go back to it. So that's one thing, amplification of the value of data. But you don't do it for nothing. What brings that value is what it benefits. How can you combine it together with applications, together with questions that benefit something? So this is what we are saying then. Can we have an environment where we amplify the value of data and build something in the middle? This is what we call the SDSC data gateway that helps us to benefit questions, that helps us to focus on those problems that are beneficial to science, society, education, engineering, you name it. Any industry, business challenges as well. So again, the problem here is, or the focus here are the problems. Can we take data related to X and use that, put that through some solution architecture that we can come up with a beneficial, valuable output? And that requires application integration. Problems are not going to solve themselves. Middleware is not going to help itself to contribute to the solution of a problem. You need to build something around that, a machinery that's around system integration of these solutions to benefit that problem. One of these problems that I love is this approach to sea spray aerosols. So these are little sprays of sea water or ocean water when the waves happen, and they have particles in them. And until recently, nobody worried about them. Ocean air was good for you. But turns out ocean air also has particles that could be not good for you. They could actually be not good for you or your environment. So this is a study that looks at individual particles in those sea sprays and tells us at scale how it affects the environment, the public health, and the ecosystems around the ocean. And when you look at this application, it has GPU-enabled molecular dynamics, which is something we are used to doing at a relatively small scale, but still at big scale for drug design. Now we are talking about environmental applications of molecular dynamics, the same molecular dynamics tools, at a larger scale. These systems are very large. And we are talking about getting the outputs of it and the experiments and doing some PCN clustering, regular methods that are not as scalable in the forms that we are talking about. And also doing some microstate optimization. So when you look at even these three boxes, there are different types of challenges here. These are traditional exascale level HPC challenges. These are big data platform-like challenges, and these are high-throughput computing challenges. So how do you integrate an application that spans through these and still continuously integrate data from experiments and applications and the results of simulations? Still use that in the almost real time to inform applications, the steering of the application, so close the loop between those experiments and applications. And while doing that, inform others for communication, reproducibility, policymakers and people like that. And by the way, if you try to do just the molecular dynamics part of it, you need 1 million plus core hours to be able to do that. So this is a board drawing, right? I liked, showing how it happened in the meeting room when we were talking about it. And those are like my handwriting in some of the parts. But when you really draw this right, it is a set of steps. And all these set of steps have different challenges in them. And we know about those challenges. For MD workflows, we build actually tools that can do molecular dynamics on different platforms at scale. And these tools are published and downloadable and usable. But how do you then now use the tool you published as a service in the context of another application? So that's the problem for system integration. There are other problems with application and system integration because in the first, and it requires multidisciplinary expertise. How do you make people talk to each other and understand each other so they can build that drawing, what goes into it, and they can turn that drawing into an integrated, scalable computing solution. You could also think about implementation of big and experimental dataset solutions, big and small, we don't discriminate, and combine that with those scalable computing solutions, and use still the individual, like the molecular dynamics tools we are talking about, combine it with methods to manage, integrate, engineer data, model data, and still put modeling and simulation on top. And also communicate the results through what we call gateways. So this is what we think is going in that situation, that application, right? We have the data lifecycle management, data science, computational science, advanced cyber infrastructure, and we talked about the SDSC data gateway and those solutions. This is this machinery, what runs it all together to solve an application. And everything I said about the heterogeneous systems, data management, resource optimization, data-driven methods, and the experts who know how to work with these and with each other in a collaborative way and to communicate to solve a solution is a challenge. So then we are really saying we have the data and problems that are related to X, and we'll benefit them. We'll come up with things that people can understand through enabling interfaces and benefit from. And the solution, the data gateway that the SDSC Data Science Hub is building is right in the middle, helping and holding hands when needed. But of course, there's a big process there. You need to enable acquisition, preparation, analysis, and reporting, and storing, and taking action on these data sets. And you need to do it in a way it's continuously iteratable, because that's how science happens. That's integratable as a quick solution, and also programmable, because when we talk about scale, we can't talk about doing things manually anymore. We need to do things, access to data, analysis at scale, and communication of results in a programmable way. What's programmable? What comes to mind is services. We need to do things that we can compose individual steps as services together, and we know what these services mean, what scale mean for these services. This is why we sat around and thought, really deeply through these. What would the services and the solution architecture be so we can enable as many applications as possible? and it amounts to this. So it looks complicated, but it's not, because normally when you do science, you work with systems, and these days you work with systems of different sorts. It's not just traditional HPC systems anymore. It's different types of commodity clusters. It's different types of specialized chips and architecture like the GPUs and FPGAs, and very, very adaptable high-end networks. Very, very adaptable active and passive storage environments. So all of these we call composable systems, and indeed we benchmark the heck out of our systems so we can understand our systems before everything else and work with the cloud environments, and we know what to ask from cloud environments to run composable services. And services are anything that we'd like to run. It could be an HPC code, it could be a big data user-defined function, it could be something like a PCA that you want to run in a scalable way, or a deep learning TensorFlow-based service that you want to run, or it could be a Jupyter workflow, Jupyter notebook that has a small portion of the solution in it. And can we expose that as a composable block is, for instance, one of the challenges we are actively looking at. And on top of it, if you know these services and how they react to scalable environments, you can then build coordination and optimization interfaces, and interfaces that you can enable others to work with these. So we call those enabling interfaces. They could be gateways. A gateway is our team you see everywhere. It could be maps, it could be information visualization environments, or it could be survey visualization environments, like the SWAV tool that we've been showing you, and I guess we'll have another demo this afternoon. So let's look at the stack a little bit, what these different bits mean. The lower stack, we have composable systems that are measured, dynamically measured. On top of that, we can build resource management that's more dynamic because we can understand what these systems are doing on a regular basis. So I'm talking about this as the future, right? But we are building the future as we are going on. We have experimental systems that we can do these things at SDSC right now. And services then are really react to the availability of the systems, and they ask for their resources. But overall, they get optimized through workflow interfaces. And we are actually building measurable collaborative services, collaboration services. So we are building test-based environments for putting things together. And the upper stack, the rest of it, what does that mean, right? Enabling interfaces, you name it. What does the community understand? What does the community like to see things through? So they can understand the application outputs. They can understand how to steer the application if there's manual feedback needed. And then data lifecycle management is a huge bit. We have a project at SDSC that manage passive and active lifecycle in a more measurable way. We have projects that look at reproducibility and integrity, like the Open Science Chain project. Again, the Suba is sitting there if you'd like to talk to her about how we are using blockchain for integrity of scientific environments and the data. So then this is an ecosystem that we are enabling, and it's really built on what we learned about needs and best practices over time, and we are carrying that to the SDSC gateway. Again, the goal is amplify the data related to X so you can benefit something. And what if X was wildfires? We actually had great benefits from that. We have now a platform that we are using big data to come up with wildfire spread and rate of direction and speed models. And what is this, right? How does it fit into this solution? When you look at that application, data lifecycle management is handled by these composable services in the background that are completely queryable. When you have such strong models of data, you can then take advantage of it in real time to curate and learn from the data that's coming on. So then you can inform, again, closed loop simulations. So in real time, computational science and models or business knowledge in general, to take advantage of what you learned from the data in real time, how you created data in real time. And when you're doing that, you need to take advantage of all you have, right? All these different tools have different computational scale and needs. So this all comes together through what we call now the SDSC gateway approach. And this is not one gateway we are talking about as a product. This is a platform to enable gateways of these sorts. So you can actually mix and match tools to come up with different solutions to solve different problems. But there are pathways through those composable systems that we know how they behave. And are we using this in other scientific applications? Yes, we are. Biology, archaeology, political science, reproducible bioinformatics, social good. These are just a mishmash of things, right? Real-time analysis of sensor streams, IoT streams, biomedical image analysis. I think satellite analysis and image analysis, Mainu and will talk about right after me. This afternoon, we'll hear about the SWA tool and how it enables a number of different applications. We'll hear from Chaitan Baru on some Arctic environments and open science chain and the blockchain approach. But here we are doing basically data ingestion, integration, integrated analytics, data discovery, and information visualization at scale. And these services run in a scalable way. So that's the message we'd like to give to you. And we'd like to definitely work with you to enable your science with our tools and with the tools of the community at large for data science. Thank you.
Thank you, Ilkay. Thank you very much. We have 5 minutes for questions. Surely there are questions about all that gobbledygook.
We've been hearing about fees and things that are big, right? And so the data is coming in
Question.
bigger,
Yes,
faster,
I knew you
a lot
did.
of different types of sources. I'm not kidding, right? This is kind of obvious. And that works
Why
as long as you've got
looking
really good people. Kind of. Until it gets too big, too fast, too much variety. So you've got to have policy, right?
Oh, so that was for Liberia, schools in Africa, let's call it. That was a collaboration with UNICEF. What we've done is we looked at the high resolution images of the Earth so we can understand how schools in Liberia or other rural zones look like. And when you use deep learning for this type of, if you build a pipeline, we use the similar pipeline for demographic analysis to understand where poverty is in India, for instance. But we helped UNICEF to identify the schools that they might not know about, the zones with the schools in Africa. And we actually won a sustainability challenge. We become second in a sustainability challenge for that was enabled by UNICEF. But it's deep learning, and Mai will be talking about that in detail. Wonderful. And the map interfaces was the communication interface. So you use the full stack, actually. GPUs, TensorFlow, Jupyter Notebooks, workflows, and maps. So that's the full stack for the enabling environment. And that's the SDSC data gateway. Right? That's what we're talking about. Jim? Thank you. And we're excited to work with you.
Data science is a lens.
So the first step really is to start to think about the system that you're building.
You know, existing
Unified space, right?
some of these things,
Devices on the sensor tool
like they may not have captured that.
At what point, where is the edge? You've got to first define the edge, right? Where is the edge?
Organize
The next step is really to move that piece left.
but not, it's an organizational question.
Closer to the point of generation of this data. This allows you to ingest it from outside, on the sheet, whatever, right? The closer you are, and you can
Yeah.
sort of transfer.
So one of the things I didn't mention about is our training efforts. We actually publicize how data science can be used through these examples in our training efforts. So it's a little bit word of mouth, but it's also in a way that trains people in data literacy. So we are actually showing these examples of how alternative data sets come together with existing examples for different disciplines. And what we've seen great success in is when we show these enabling interfaces, not the rest of it, our users get excited about it, and they are actually starting to think about how can I do that? If they use satellite data for X, can I use it? I recently worked with a geothermal researcher, and it's under the world, under the earth, right? But then she was like, oh, we can also use maybe satellite information to look at the earth in a way that we can reduce to zones for boreholes, and then start looking at it. So when you start showing that they can have access to data in a programmatic way, and this is possible, I think communities understand how they can use this. So that's been our approach, and there are probably better and bigger approaches to that, but we are also about controlled growth as we go through. But I think overall, building a solution architecture like that can scale, so we can then engage with as many users as we can is what we focused until now, and we are starting to see benefits of that. Thank you very much.